This is a mini lecture to discuss the concept of the this, THIS, keyword in Java and what it means in relationship to object-oriented programming. To get started, I'm going to talk a little bit about my car. In front of us, we have blueprints for a Honda Element. I really like my Honda Element. It's a fun car, and I'm really sad they're not going to be making them anymore. So, what is this? Well, this is a potential car. In other words, this is some rendering of some basic blueprints for a Honda Element that I was able to find out on the internet. But this isn't my car. This is just a general concept of a Honda Element. Now let's take a picture of my car. And here we go. There's my Honda Element. And that's me sitting in it a couple summers ago enjoying the nice warm weather at the beach. Now, what do we do with these two concepts? First of all, we need to understand a couple things. That the car you're seeing with me in it is my car. It's Jason's car. It is a concrete instance of a Honda Element. You know, somewhere at a factory, someone built this car. It rolled off the assembly line. It went to a dealership. I went there and I bought the car. But if we go back and take a look at the blueprint, what we have here in this blueprint is a car that's yet to be built. It's a concept. It's a design document. It's something to be taken to the assembly line and for equipment to be machined and people to learn how to assemble an automobile. This is not something you can drive. This is not something you could, well, I guess you could sell the idea of the car, but this isn't a car. It's a potential car. How does this relate to object-oriented programming? Well, the blueprint for the Honda Element is similar to the class files, the .java files that we're writing this semester. Class files define the concept of our objects. They define the properties and behaviors that those objects have. When we go ahead and we call the new keyword, what we end up with is an actual object based upon that blueprint that we built in the class file. Just like I have an actual Honda Element that was built from a set of blueprints by a bunch of people on a manufacturing line. So, how does this relate to this idea of this? Well, when you're looking at my car and you see me in my car, it's pretty straightforward to say, well, that's Jason's car. But if we go back to the blueprints and we look at these blueprints, whose car is this? Well, it's nobody's because it's a generic car. It's a generic concept of a car. So how do we say, when we're just looking at blueprints, how does a designer of a car or an architect of a building say when they're talking about a blueprint that, hey, when this thing is actually made, what I want you to do is refer to, you know, that specific car that has rolled off the assembly line and not maybe say the one behind it. And a good example of where this might happen is, you know, think about something that's unique to each car that might roll off an assembly line. And what I've done here is I've gone ahead and I've written a class that's going to help us work through this idea. So keep in mind that I've got a blueprint for a car and I drive an actual car that was built from some blueprints. So now let's take a look at some code. I have a class here and it's called Honda Element. So this is equivalent to our blueprints. This defines a really basic class for some generic abstracted concept of a car. Now, again, this is not a car yet. This is just the blueprints. I've yet to call new on it. I've yet to set it up in the driver. I've yet to build it. And so what you'll notice at the top is I've decided to just put two properties in this object, two instance variables, one called mileage and one called gas to track the number of miles it's been driven and to track how much gas is in the tank. These are private to enforce encapsulation. Now if we look, I've got a couple of different things going on here. So this is not yet a class, like it hasn't been created, like it doesn't have a name, like I can't say that this is Jason's car. This is just a generic concept of a car. So when I create any instance of this class, so in other words, when I create any car Honda Element item by calling new on it from this class, what I want to do is to be able to set its mileage and set how much gas is in the tank. I'm just going to represent the gas tank as being a percentage full between 0 and 1. You know, you're going to notice in this constructor that I've gone ahead and I've written things a little differently. And what I've done is I've written this code to be very verbose. In other words, I'm not taking very many shortcuts in the Java language. I'm trying to write this in a fashion that's extremely readable and goes and doesn't really try to be, you know, concise in any way, shape, or form. Because a lot of times I think people don't understand the this keyword because many times we don't need to use the this keyword. So a couple things here I've done to force this concept on us so that we can get this idea. First of all, you'll notice that I have a parameter named mileage and a parameter named gas. These are related to the constructor. But then you're going to say, well, wait a second, Jason, you have a property named mileage and a property named gas. How can the Java runtime discern between two variables that have the same name? Awesome question. So here's why. Whenever you declare a variable inside of a method, that variable is locally scoped to that method. In other words, it only lives inside that method for the length of that method call. So this variable named mileage will only live long enough for these 2 lines of code to execute, and then it'll be destroyed. And this variable mileage is going to be local to this method. Just like this variable gas will be created, it'll exist for the length of this method's runtime, and then when this method is over, it'll be destroyed. And you say, well, that's great. But then how do I reference these class level variables that have the same name? Well, here's the deal. The this keyword is how an object refers to itself. Just like I would refer to myself as me, I would not probably refer to myself in the third person as Jason, because that would be like a bad episode of Seinfeld. But in this case, many times we refer to ourselves as me, or myself, or I. Well, an object needs a way to refer to itself as well, because objects oftentimes don't know their names, and we'll see why in a second. They just happen to know that they're, happily existing in this world, and they can refer to themselves as this in Java. Other programming languages use other words. So the concept here is I have the keyword this, and it's a way for saying, look, once you create a Honda element, once you take this blueprint and you create an actual car, what mileage do we want to set? Well, we want to set the mileage for this instance of the Honda element. In other words, whatever Honda has just been created. It's like saying me. So change my mileage to the mileage that's passed in, and change my gas to the amount of gas that's been passed in. Well, what do they mean by my? Well, this, or in my case, this, it doesn't mean anything until this concept, or this blueprint of an object, has been converted into an actual object via calling new in our calling code. So in this case, how can I discern between the passed in variables that have the same name and the instance variables that have the same name? Well, simply by saying this.mileage and this.gas is enough for this object, when this constructor is run, to say, oh, go to my instance variables, go to this object's instance variables, and set the value for mileage. If you don't put this on that mileage variable, it refers to the locally scoped variable mileage. So just by saying mileage, what happens is the compiler's lazy, in a sense. It's going to see a variable name, and it's going to say, well, are there any variables named mileage inside this method? Yes, okay, use those. It's not going to go look outside the methods right away. So what it'll do is, if I just say mileage, it'll say, oh, there's a variable in this method called mileage, go get it. But if I say this.mileage, it says, well, go to the instance variables and see if there's a variable called mileage. In other words, look at the current object, me, this, and get its mileage variable. Same thing for gas. Go to this object's instance variables and get its gas property and set it to the gas variable that has been passed in. So again, 2 variables, same name, different scope. And by scope, I mean where is that variable declared and who can see it. The same concept works for method calls as well. So if we scroll down, and you've probably been already looking at this, you'll notice that I've got a private Boolean method called checkGas. And all this is going to do, I think this works, I didn't really test this too vigorously, it's going to look at the current instance variable gas for this current object and make sure that we've got more than 0.1% of gas in it, and return true or false based upon that value. And you'll notice that on line 12, I have the ability to call that method using this.checkGas. Now, a lot of you are saying, well, geez, Jason, why did you put this on there? I've never done that before. And here's the deal. The assumption is if you don't put the keyword this into or in front of a method or in front of a variable, the program runtime is still going to go ahead and look for methods. So what it's going to do is it's going to say, well, okay, look inside this method named drive. Is there a method declared inside this method named checkGas? No. Okay, now let me go out to the class level. Is there a method at the class level named checkGas? Yes, there is. Call that method. If there wasn't, it would continue till it exits the class, and it would give you an error because it'd say, hey, I can't find a checkGas method. All you're doing by putting this in front of the method name is saying, hey, look inside of this current instance of the Honda element class and call the instance variable checkGas. It's a way to basically help and define in a more clear fashion the scope of the variable that you're calling, or the scope of the method that you're calling. And again, up to this point, you probably have never not, or you may have never used the keyword this, because in many cases it's implied. You don't need to use it. Like if somebody came up to you and said, give me $20, they're implying that they're talking to you because they're making a statement directly to you. They don't have to come up to you and say, Jason, give me $20. Because they don't need to make that statement. They by making that statement to you, it's implied that they're dealing with you. So the idea here is this is a way that objects refer to themselves. Let's take a quick look at what this looks like in the driver. Inside of the Honda Element driver, what I've done is I'm going to create a car. I'm going to give it a name. So it's going to be of type Honda Element, and it's going to be called Jason's Element because it's my element. And I'm going to make a new Honda Element object, put 36,000 miles on it, give it a full tank of gas, and then I'm going to tell my Honda Element to drive. So notice in my driver, I give my variables a name. Well, realize a couple things. Variables are really just named references to memory locations. And so what's interesting is the Honda Element object that's created by my constructor and that's returned and stored in this variable, it doesn't know that it's called Jason's Element. It just knows that it's stored somewhere in memory, and it's referenced in the JVM by a hexadecimal memory address. But on my end, because humans think better in terms of language than numbers, instead of having to call the explicit memory location for that object that's returned, we get the convenience of the programming language allowing us to name a variable and then call that variable by name. But what's interesting is the object has no idea that it's called Jason's Element. The object just knows that it exists on the heap at a specific memory location, and we know that the variable called Jason's Element actually maintains a reference to that memory location. So what I do then is I just say, hey, Jason's Element, call your drive method. And when I call the drive method, this specific instance of the Honda Element class goes ahead and reduces the gas available in the car, and then it also goes ahead and adds 30 miles to the odometer. It's not the world's best class, but it's just to make a point. And so in our case, we refer to things in our calling classes by their name. But when we need to refer to the class inside of the class, in other words, when we don't have a concrete instance of the class, in other words, we haven't called new on it, we don't have a reference variable that we can just give the name of that reference variable, the object, what I need to do is inside the class, whenever the class needs to refer to itself, whenever it says, hey, my variable mileage, my method check gas, I have to use the keyword this. So this is a way within a class for a data type which has been defined, just like a blueprint, and has yet to be created, can refer to itself. Let's talk a little bit about the process of compiling code from Java into the format that the machine needs to actually execute and run that code. So let's think about talking to a computer. First off, we could try the Star Trek route and just say, for example, like our clip art friend here in the slide, computer, print hello world. And, you may have used Dragon Naturally Speaking or one of these other programs, but what you're going to get back is a big question mark from the computer, because computers don't speak English. They speak machine language. All right, so we've got to get this straight, that computers speak one language, humans speak another. We need a way to reconcile this difference. And remember that machine language, simplified, is the native language of a computer system. And machine language is usually tied to the system architecture. In fact, it's pretty much always tied to the system architecture. So Intel chips have one set of machine language. Okay, ARM processors, like are found in the iPhone and the Palm Pre and those types of smaller devices, have their own machine architecture. The PowerPC chips from IBM have their own. So there's this low-level machine language that the hardware expects to have the information presented in, so it understands what to do. So we could learn to speak that machine language, correct? We could learn to speak zeros and ones, and people actually do this. And if you ever go ahead and take an assembly language class, you'll get pretty close to speaking to a computer in zeros and ones. And there's a great history of the Apple I, built by Steve Wozniak, where he could actually program in low-level, technically in his case hexadecimal code, directly to the hardware because he built it and he knew exactly how everything was architected, and he could speak to the machine in its own language. But this isn't really practical, I mean, we could speak to the machine like that and it would say hello world, but the amount of time it would take us to learn to speak machine language at the lowest level would be a bit ridiculous. And if you really think about it, humans speak better in words than they do in numbers. We want to speak or program in a high-level language, okay? And Java is a high-level language. It abstracts the complexity of the machine. I oftentimes simplify this too by just saying like, okay, look, high-level languages are a little bit more like native human languages, and in our case, like English. So high-level language allows us to speak in a way that we're more comfortable with, and then we have to have a process to get that high-level language into a format that the computer is comfortable with. The ideal here would be that we would say, hey look, computer, print hello world, and the computer would understand exactly what we're saying from our high-level language and produce the output hello world. How do we get from human-readable language to machine-readable language? We introduce a program called a compiler. And a compiler's job is to take one form of a language and convert it to another language. Okay, there's a really generic definition that we want to go here with a compiler. It converts one language to another. It's a program. You know, if you're on Windows, it's a .exe file. It's going to actually convert high-level language into low-level machine language for us. And you might hear that a compiler converts high-level language to machine language, but again, stick with the generic definition. It converts one language to another, because there's cross-compilers that convert, say, Visual Basic version 6 into Visual Basic.NET, and you know, there's also some other compilers that do things like reverse compile that'll take machine language and try to build it back into high-level human language. So the general idea here is it's a program that converts one language to another. In our case, we're dealing with Java. So we can say specifically that the Java compiler's job is to convert Java source code into what's called bytecode. So we have to talk a little bit about these terms, but we're taking human-readable Java and we want to convert it into something that the machine can execute. Now, there's this little bit of odd thing that I mentioned last week about Java, okay, and it deals with this process or this intermediate step of compilation called bytecode. The machine language of the Java virtual machine is called bytecode. And if you've pressed the plus sign in JGrasp, you've probably noticed that it generates what are called .class files, or not what are called, but what are .class files. They have the same name as your .java file, but they just have a new extension called .class. These are actually the compiled versions of the Java bytecode. Well, these are the actual compiled versions of the Java program that you have written. They are in the proper format to be run by the machine. Now here's what's different. Let's go back a little bit. If we look at this case, the question here needs to be, what language am I writing my computer print hello world statement in, and what type of compiler am I using? So for example, if I'm writing in a program language like C, or C++, I would write my computer instructions in C. The compiler would then convert them directly to machine language for the operating system and target processor system that I'm on. Pretty straightforward. Convert directly from programming language into machine language. That's how a directly compiled language works. Java is a little bit different. You're going to say, well, bytecode. You're saying bytecode, you're not saying true machine language. Why is that? What are these .class files? I mean, are these ready to be run on the computer? Well, let's talk a little bit about how Java actually works. Java is like a unique type of programming language in that it tries to abstract the hardware from you. I mean, think of the brain load necessary for a programmer who wants to program his application so that it runs on every computer in the world. Well, think of the limitless combinations of operating systems and processors, you know, that are out there. I mean, there's many, many, many of them. If you go to Wikipedia or Google and you just look at, you know, Google CPU or Google, operating systems, you notice that there's a limitless combination. Sun came up with this idea within Java of having a virtual machine. And virtual machines have been done in the past, but in our case, it's really like a simple computer that abstracts the entire computer system, and its job is to run bytecode. The JVM is like a tiny computer written in software that is guaranteed to be the same on every computer that you ever have it installed on. So think of that. Instead of having to worry about all of these multitudes of combinations of different hardware and operating systems, you can write to one computer. You're guaranteed that the Java virtual machine should work the same on every computer that it's ever built for. So the Java virtual machine is our Java runtime environment. It abstracts the computer and executes bytecode. So let's talk about how this works. Okay, computer, print hello world. We write that in Java. We pass that source code to a compiler. Once the .class files are created, we've got bytecode. The bytecode files are then, when we're ready to run the program, passed to the Java virtual machine, which you can think of as a tiny little computer that's written in software that's guaranteed to be the same on every computer. It abstracts or hides the complexities of the actual hardware. The JVM then takes the bytecode and converts the bytecode into native machine language for the system that you're on. What's awesome about this is you don't have to worry about the machine code of the native system. You just need to know how to write to one computer. In your world, your brain is happy. You can go home, well, I was going to say you can go home at 5 o'clock because you don't have problems to deal with, but programmers always have problems to deal with. The power here is that you write the program to only one computer, the Java virtual machine, the Java runtime environment. Now, can there be different versions of the Java runtime environment? Sure, it gets updated like any other software program. But if we go back, we don't need to worry about that last component. This is all we need to worry about. The Java virtual machine at the end of this chain. Who deals with the final part? The computer and the machine language conversion from the Java virtual machine over to the native machine? Sun Microsystems. They're doing what I would consider the hard work, so you can just jump right in and write really cool applications and do fun stuff. And eventually at the end we get, hey, hello world. So look, the Java virtual machine is an interpreter. Its job is to execute a programming language. In Java, the Java virtual machine is an interpreter that executes bytecode. We pass bytecode to the interpreter. Could we pass Java source code directly to the virtual machine? I mean, could they have made that decision in the design process to actually just convert source code directly to machine language? Sure, and many languages that are interpreted like Python or Perl do just that. They'll take the source code directly. There might be an intermediate compilation step in there that happens actually at runtime, but they do that. Now, in the case of Java, a lot of enterprise applications are going to be written, and a lot of people who want to deal with closed source applications where you cannot only the people inside the company are allowed to see the source code, and the bytecode gives them a little bit of security in that you're not just handing out your source code, which in some companies people feel that proprietary source code is a business advantage. I'm kind of an open source advocate. I don't agree with that, but the bytecode also gives you some level of protection for your intellectual property. Another term I don't like too much. So the idea of the Java virtual machine is that it's an interpreter. It takes the bytecode and converts it at runtime, at the time it's requested to be executed, into machine language. We could use probably an outdated term at this point, but worm to explain the Java programming environment. You basically write once and run many. What's really cool about this is if every Java virtual machine is guaranteed to be the same on every machine, you can write your program one time, and then you can put it up on your website or sell it, and it should run the same on a Windows machine or a Mac or on a Linux machine, or depending on if you appropriately program it to not consume tons of resources on a cell phone. I mean, the idea here is you can get a business advantage, and that's the thought behind programming languages like Java that utilize Java virtual machines, is that you write the program one time, and you write it to this Java virtual machine, and then that Java virtual machine, if it exists on a platform, like if there's a JVM for Solaris running on a Spark processor, which I'm sure there is, then it should run exactly the same as running Windows on an Intel processor or running Linux on a PowerPC chip. Write your program one time, run it in many places. People say, Windows is the primary market share leader in most places, and it is, but you figure that's like 80-90% of the market. You're still 10% of the people out there that you want to target and get their money if you're writing an application. I mean, your store shouldn't turn away 10% of all people who want to come in and patronize your store. So same thing with your applications. You want to get out there as much as possible. So look, here's the takeaways for this lecture. You only need to learn to code for one computer, the Java virtual machine. The Java virtual machine is a piece of software written by Sun Microsystems. Its job is to take bytecode and convert it into a format that is understood by the underlying system. It converts it to the machine code and native system calls that the underlying system needs to get the job done. You don't have to worry about that. Life is good. Just like driving your car, you don't need to be a mechanic when you're a Java programmer. You only need to know how to work with the JVM. You do not need to know how to deal with the underlying computer systems of every computer out there. So look, Sun Microsystems really handles the hard work of abstracting the computer. I mean, for every operating system and every hardware architecture, they need to write a Java virtual machine. In the case of Apple's JVM, I believe Apple actually writes that themselves because you can license and build your own JVM. So now that things are growing towards the open source end with Java, I think you're going to see a lot more JVMs out there that are optimized and probably a little bit, maybe some more flexibility in that area. But anyway, the JVM handles the hard part. Okay, the side that faces you always looks the same. It's the exact same computer, but the side that faces the computer is always customized to work specifically with that system. And think about it. Sun needs to know how Windows, Mac OS 10, and Linux all work together with the systems that underlie it and different architectures. You don't. You just need to know Java. Very cool, right? A couple other things in terms of writing our programs to go over this process. We write Java source code. We click the plus button in JGrasp to compile it to bytecode. We then execute the bytecode, which is passed to the Java virtual machine to be executed. The Java virtual machine then converts the bytecode to machine-specific code so you don't have to. And I say usually here because there are ways to make specific calls. You can actually write Java programs that only run on Windows. But I would probably argue if you're going to do that, you shouldn't be using Java. Somebody could always disagree with me on that, but just something to think about. So the JVM converts the bytecode to machine-specific code, handles that really difficult part. And finally, if you think about it, right, you should only need to write a program once and you can deliver it to multiple systems. That's pretty powerful from a business standpoint. It affects your return on investment. The only thing you need to do is just make sure your users have the correct Java virtual machine installed. So if you're writing to Java Virtual Machine 1.6, like we are in this class, make sure that they've got that version installed. You need to just really make sure that that's taken care of. And most people, Java is pretty ubiquitous at this point, and most people, if you've got a Windows machine, you usually see that update, or if you have Java installed that says, hey, there's a new version of Java out. And most systems will handle keeping around older JVMs, but you just have to work to make sure that within that minimal number of Java virtual machines that are available out there, that your target user base has exactly what they want installed. Just a quick comment, I wanted to give some credit to that nice Macintosh picture that I got off Flickr. It was available through a Creative Commons license, so it was available for nonprofit use, and I wanted to give a link to the original photographer to their website on Flickr. So that's the process of compiling. Hopefully this is helpful. If you have questions, post them to the discussion board and we can discuss in more detail. The first video lecture for this course is going to focus on the tools that we're going to utilize all semester for writing Java programs. The first thing we're going to do is look at the tools, how to obtain the tools, and then we're going to talk about specifically what role each tool plays in the development process. From there, we're going to move to actually write a program and get our feet wet and hopefully have a little bit of fun, and you can see how exciting it is to write a program. I think it's really cool what it's like to give instructions to a computer, what a programming language looks like, and also what the corresponding environment looks like that we're going to utilize to build a program. So the first thing I've done is I've navigated in my web browser, and I'm using Firefox, and I am at java.sun.com. The Java programming language is maintained by Sun Microsystems. Primarily, it's been open sourced lately, but Sun is still the driving factor in the day-to-day maintenance of Java, also with defining the standards. That might change over time because Java has become open sourced, kind of like Linux, and it's being worked on by a community of people. Recently also Sun Microsystems, I believe, was bought by Oracle. I've been trying to avoid any type of tech finance news recently. So that might also, if that gets approved and once that is finalized, some other unique things may happen with Java at that point. But today we're going to look at Java as it exists. It's a popular programming language and it's something used pretty heavily in industry. So the first thing we want to look at is what do we need to download. If you go to java.sun.com and you navigate to the main page, which is where it drops you off, you're going to scroll down a little bit and you'll notice that at the top we see APIs and we see downloads. There are a couple of different options here, so I'll walk through and talk about these a little bit. We're most interested in the download called Java SE. Okay, this is the Java Standard Edition development environment. Actually, the first three things here in this list that start with Java are what are called JDKs, or Java Development Kits. Okay, so what does each one stand for? Well, Java SE, like I said, stands for Java Standard Edition, and that means that usually we use the Standard Edition development kit for building things like regular desktop applications. If you wanted to build an accounting application or maybe an application to track your CDs, this would be the right place to start. Java EE stands for Java Enterprise Edition, and this is for writing network-aware apps. So if you do any online banking, applications that touch the internet that need to connect to databases, I would say the bulk of Java development that I'm aware of, or my friends that develop in Java actually do enterprise environment development because they're dealing with large corporate systems and interconnecting those systems. And then finally there's Java ME, which stands for Micro Edition, and this is utilized for resource-constrained devices. So if you've ever had an older cell phone and you've done some Java development or downloaded applications with it, like this would be the type of Java development kit that you would want to download for building those applications. This is not the same development kit used for, if you know a little bit about Java, Google's Android telephone uses its own SDK. It's all based on Java. Maybe later on the semester we can take a look at that. Anyway, let's go ahead and click on the Java SE link. This is going to take us to the Java Standard Edition download page. And you're going to notice that we're dealing with Java Development Kit 6 Update 14. So what does this mean, JDK 6? Well, again, JDK stands for Development Kit because we are developers. We are going to write programs. We're not just going to run them. Okay, we're going to need to download the newest development kit. If we just wanted to run Java programs, we would go ahead and we would download the JRE, which stands for Java Runtime Environment. Conveniently, when you download the JDK, it also includes a JRE. What's the difference? The JDK is for developers. The JRE is for end users. So you will use the JDK to write applications. If you want any of your friends to run those applications, you would ask them to download the Java Runtime Environment. If you've ever run a Java program on your computer, you have a Java Runtime Environment available. And most of the time people have the Java Runtime available to them because it's been provided through their web browser, or at one point or another you've wanted to run a Java application with your web browser. So we want to go ahead and download Java Development Kit 6 Update 14. This is only for those of you using Windows. If you're using a Macintosh, you are going to utilize the most recent version of Java that comes with your operating system. When you're on a Mac, you don't kind of want to mess with Apple's system load, so what we're going to do is just go ahead and utilize whatever version you have. If you're running a newer version of Mac OS, you should have at least Java Development Kit 5, but more than likely you should have Java Development Kit 6 if you have one of the newer versions of Mac OS 10. Why is it called Java Development Kit 6? This is a little bit confusing. 6 actually stands for 1.6. The previous version was Java Development Kit 5, and that actually stood for version 1.5. If you look at older versions before that, they were actually called like 1.3, 1.4. This is kind of a case where the marketing department, I think, has done a little bit of damage to Java. So anyway, we're using Java 6, which really is 1.6. And that's the version of the development kit we are dealing with. So you want to go ahead and you want to download that and install it on your machine. Once you get Java downloaded and installed on your machine, if you're running Windows, even though it might not require you to do this, I would recommend rebooting your computer. Once your computer reboots, you want to navigate on over to jgrasp.org, and this is going to be the piece of software that we're going to utilize this semester for writing our programs. So the Java Development Kit provides the functionality necessary to build Java programs in terms of the Java Foundation frameworks and all of the underlying Java libraries, the pre-written Java code that we're going to need, but we still need a way to go ahead and write our own programs. And in this case, we're going to use what's called an Integrated Development Environment. The Integrated Development Environment, or IDE, that we're going to use this semester is called JGRASP. It is a very lightweight IDE. It is built for education. It's rather nice. It's not something you would see out in industry. But what is nice about JGRASP is that it's a really easy tool to get started with. Probably the most popular integrated development on the market would be Microsoft's Visual Studio. But that has some Java support, but not the greatest, and we want to actually utilize JGRASP for this semester. Later on, we'll look at Eclipse, which I think is the best Java development environment out there, and I really like that. There are tons of integrated development environments, and all they really do is provide all of the tools necessary to build a program from the user perspective. A good way to think about it is that the Java Development Kit, or the JDK, provides the stuff the computer needs to build the program. The IDE provides the stuff that the human needs to write the programs that are necessary to run. So in this case, all you need to do is click on the download link on the JGRASP homepage. You'll scroll down And remember, you've already installed the Java Development Kit and rebooted. And then all you need to do is grab the newest version for your operating system. If you're using Windows, be sure to grab that version. Mac OS, same deal. And also, if you're using Linux or Unix, you'll know how to figure this out because I'm assuming you're using Linux, you know what you're doing. Up to this point, all of our programs have required that we hard code the values that we're using into them, but it'd be a lot more fun if we could actually ask the user to input some data. So let's talk a little bit about how we can do this. Up to this point, the only object that we have utilized is the string objects. Remember, objects at this point in the class are just kind of like special data types that can do a lot more stuff. And how do we know what they can do? Well, at this point I tell you, or the book tells you. So let's go ahead and work with a new type of input object. Basically what we want to do is get user input. And we're going to talk about a function that was implemented in Java 1.5 and newer called the scanner object. So I'm going to go ahead and type a line. I'm going to ask that you guys do the same thing. And we're not going to talk too much about what's happening here. But essentially what I'm going to do is initialize an input scanner so that we can utilize it and ask it to do work for us. You don't really need to know about too much of what's happening on the right hand side, but this is object initialization in Java. What I'm actually doing is creating a variable called scan, and that's going to hold the object whose job in our program is going to be to actually read input. What goes into the variable named scan? Well, a data type of an object that is of data type scanner. So get user input. How we're going to do that? First thing we're going to do is initialize a scanner object to do the work for us, because we don't want to have to do this work. We don't want to have to write this code. It's already written for us. One of the other things that we need to remember to do right away too is, and I'll enable line numbering here, is I need to go all the way up to the top of my code. Now, getting or reading data from the command line is not a default piece of functionality in Java. You need to ask for it. And Java does this so that you're not having, it doesn't want to present to you all the features that you absolutely need unless because basically that gets to be overwhelming. So some features in Java you have to ask for or you have to import. So in this case, I'm going to actually import the scanner functionality. And basically what you do when you import the scanner functionality is you're telling Java that, hey, I want to use this command line input functionality. Notice I put it on line 1. It comes before everything else in my code. Notice I use the import keyword, and notice I follow that up with java.util.scanner semicolon. Again, where does all this functionality come from? Later on we'll look at the API, which is the application programming interface for Java. But right now, the functionality that I'm presenting to you is the functionality you should use, and it's really the only functionality we want to focus on at this point. A couple weeks we'll start to grow exponentially in terms of the functions of Java that we'll look at. So to get this working, I need to put this line on my code first, import, and then on my other line, inside of my main method, I need to go ahead and I need to initialize my scanner object. So this is going to handle getting our object data. Now what we're going to do is I'm going to make a variable that's going to hold a string, and I'm going to call it user input. So what I'm doing here is at the top of my code, I'm going to initialize all my variables. So I'm going to initialize my input. Now what I'm going to do is I'm going to go ahead and I'm going to ask the user to enter some information. What I actually need to do first is just print a statement that says, please enter your name. And I won't put a semicolon on that one. We'll just put a period. And then what I need to do is ask the user. So this is like a prompt. We don't want to just have a blinking cursor. We want the user to say, oh, hey, they want me to enter my name. So let's go ahead and get that information from the user. First thing I'm going to do is I'm going to assign whatever input the user enters into my user input variable. That's why I created it. So it's a storage location that I'm going to use later on in my code to hold information. And the next thing I'm going to do is ask the scanner object. Notice we've done this before. We said system.out.println. So I'm going to say scan.out. And scan is the name of the variable that holds my connection basically to the command line so I can get input. And again, this is an object that we're going to ask to do some work for us. So I'm just going to say scan.next. And you'll notice that scan.next is a feature that lets us actually get information or string data from the command line. And this is how Java handles this. Other program languages, do this a little bit differently. And you can find this stuff in the book as well. So this is kind of just a recap of how those components work. Once I get the input from the user, this reads the data in. Then what we can do is we can print a customized welcome message to the user. And how are we going to do that? We'll say welcome. I don't know why I put a space in there. We'll use concatenation. I'm going to glue the string welcome to the value currently stored in user input. So I'm going to go ahead and compile this and run it. Notice when I run the program, what we get down here is it prints please enter your name. So the first things that happen is it sets up my scanner object, it initializes my user input variable, and then it comes down to line 14 and it prints my name. Or it says it prints please enter your name. And I'm going to put JSON in there. Input in Java, you enter into the run IO window of JGrasp, type in what you would like to enter, and hit return. Once I hit return, the value that I entered in this line of code is stored into this variable, and then I concatenate it together with welcome. So let's walk through the process one more time. When I hit run, the program initializes my scanner object. It also initializes a storage location to hold the data. On line 14, I prompt the user for the type of data that I want because it's kind of annoying to get a blinking cursor and no idea what I want to get. When line 17 is reached in my program, it actually stops the program from running. The line user input equals scan.next stops the program from running. It's actually the call to the next method. So scan.next stops the program from running, reads the data, stores the data that I type into user input. Once I hit the return key, the program continues execution, comes down, and prints the customized welcome message. We can use this to get other types of data. So in our case, next is utilized for getting strings. If we wanted to actually get other types of data from the user, notice that the storage location here I used as a string, and it corresponds with user input, getting a string from the scan object. So next reads in a string. If you want to read in any other type of number, to get an int, use and to get a double, you probably already guessed it, and I'll just leave those in the code for you to play around with. Problem is, user input is of data type string, so the reality is if you wanted to utilize those other components, you would need to change the user type, the data type of user input to int or to double. So this is the really basic framework for reading data in from the user. We'll work with this throughout the semester, and if you have any other questions, please don't hesitate to ask. In this lecture, we're going to talk about variables. What is a variable? Well, if you think about your computer, there's constant electricity running through it. And if you've ever seen The Matrix, you can kind of think of those green letters falling down the screen, or you can think of a river. And sometimes we want to take a piece of data and we want to hold on to it. In other words, if we didn't hold on to the data we were interested in, it would get washed away in all of the bits and we would not have it to utilize in our programs. So what we need is a way to set up a storage location in memory so that we can have a variable that we can access later. So it's a named location in memory. And specifically, it's in our RAM, in random access memory. What we're going to do is we are going to ask the computer to reserve a space in memory so we can store a value in it, and then all we need to do if we want to access that variable at a later point is we need to go ahead and ask for it by name. Usually we name variables logically based upon their use. A couple other things. So let's go. Let's declare a variable. What this basically says is, hey computer, I need some space and memory. So I'm going to go ahead and I'm going to declare a variable called, I guess we'll call it tax. And I'm going to actually not just put the word variable there, but I need to, whenever you declare a variable, Java is what's called a strongly typed programming language. And what you need to do in Java when you declare a variable is you need to go ahead and you need to tell Java what type of information is going to be stored in there. And basically, what is the data type that's going to be stored into that location. And in my case, I'm going to put double here because I'm going to store tax. So it says, set me up a location in memory called tax, and be aware that the only information that is going to be stored there will be of type double. Now I've declared the storage location and it is available in memory. Now I can go ahead and I can initialize the variable. And what I can do is I can set the tax, and this is Pennsylvania, so we'll go for 0.06 tax. Notice I'm ending each line with a semicolon. Important. I mean, at this point we've seen it a bunch of times, but it ends each simple statement. So what's happening on line 9 actually goes ahead and sets up the storage location, and then what happens on line 12, it puts the initial value into that location. What's in the location? If I don't initialize the variable, nothing, junk. Well, actually in Java it'll put some false value in there, but if this was C or C++, you'd have whatever value was in that location in memory previously. So it's kind of like if you've ever rented a car and they don't clean it out, you get all the junk that the person who rented it before you got, and that's just not fun. In Java, it'll actually clean things out for you. But just one point. You can actually do both these steps at the same time. And what I'm going to do is make another variable that holds an int, and I'll just call it high score, and I'm going to set it to 1,000. So notice I can both declare and initialize a variable at one time. The only time you need to put the data type for the variable is the first time you declare the variable. So it says, hey, give me a storage location. It's only going to hold doubles, and I'm going to refer to it in the future as tax. So here's what's kind of cool. We want to go ahead and we want to print this out. All I need to do now is tell the computer where the data is stored, what storage location it's stored in. I'm going to go ahead and ask for the storage location named tax, and it's going to go ahead and it should print out 0.06. And we'll actually do this twice, and we'll have this one print out high score. And then what we'll do now is we'll go ahead and compile, and we'll print it. And notice that we get the values that we had stored in those locations just by asking for them by name. So we set up a named location in memory, we tell the computer what type of data is going to get stored there, and then what we do is we go ahead and we ask for that by name. We can also change these. So let's say, we'll make this a little bigger. The tax gets modified. So we can reset tax to be 0.10, which I hope doesn't happen, but let's say the tax gets changed. Notice that our programs get executed top to bottom, left to right, just like we would expect from reading. And you'll notice that in this case I initially set the tax variable to 0.06. Down here I'm going to go ahead and I'm going to change it to 0.10. Whenever you change a variable's value, it overwrites the old variable. This is not going to add 0.10 to 0.06. It's actually just going to overwrite. So whatever was there initially gets kicked out. So I'm going to recompile, and I'm going to run it. And now you'll notice this time the value that gets printed is 0.1, not 0.6. Why? Because after I initialized the variable, I came down here on line 18 and I changed the value. Kind of cool. Kind of interesting. So let's see what else we can do with variables. First of all, notice our output is kind of boring. It's just 0.1 and 1,000. So how can we modify our output? We can use concatenation. So we could put, sales tax in PA is, and now we can use the plus operator. And remember, in this instance, the plus operator means to concatenate. It's going to take the string on the left and add the string on the right. And here we'll put, current high score is, and now what I've done is I've effectively labeled my information. So I'm going to compile this, I'm going to run it, and get everything in one window, and now notice how the string sales tax in PA was glued onto the value stored in the location called tax, and same thing happened to the high score. So this process of concatenation allows us to, we'll put that here, concatenate two values for readability. In other words, what this just does is it lets the end user realize that they know what the data is. It's never good to just get numbers printed out to the screen. We want to think a little bit about the user experience as we're writing these programs. All right, so a couple other things we can do. Not only can we change a variable, I'm going to comment this out. Let's say we want to take the current value in text and we want to add something to it. So instead of changing it to 10, let's just say we want to add 0.2% to it. We can actually change values. On the right-hand side, we can actually put mathematical operations. And in this case, what I'm going to do is add a value to, let's just go back and say add 0.02 to the value stored in text and store the new value back into text. Here's what's interesting. On your computer, just like in regular math, mathematical operators have an order of operation. In this case, everything on the right-hand side of the equals sign happens first. Okay, and this is actually not the equal sign, it's what I would call the assignment operator. Okay, because in this case what we're doing is saying take everything on the right, perform any math if necessary, and then assign it to the storage location on the left. So in this case I'm going to take 0.10, I'm going to add I'm going to take 0.06 because I commented out line 18, add 0.02 to it. It's going to take 0.06 plus 0.02. It's going to get the value 0.08, and then when it's done, it's going to kick the old value out of tax and store 0.08 in that. So what we say here is right side happens first. So items to the right of the assignment operator happen first. Then assignment occurs. So let's go ahead, compile it, and run it. So you'll notice that I get on line 26 that sales tax in PA is 0.08%. It's not, it's 0.06, but why did this happen? Well, up top here, we set tax equal to 0.06. We read the value 0.06 from the variable, added 0.02 to it. The computer temporarily gets the value 0.08 and stores the variable 0.08 or the value of 0.08 back into the tax variable. And then the next time we access the tax variable, it prints out the most current value, which is 0.08. So this idea of adding and working with values in variables is pretty important. We can do the same thing with high score. Let's take high score and let's just take the current value of high score and divide by 10. Why am I doing this, by the way? You can think of this as really reusing variables, just kind of like you would in an environmentally friendly setting. You don't want to waste natural resources. You also don't want to waste computing resources. So in this case, it's really helpful that I can reuse an existing value. So that's some basic components of working with variables, some basic components of concatenation and printing out values. Let's take a look at the very basics of inheritance in Java. What you see in front of you is a class called item. It represents a generic class of sellable goods. So, anything could be an item, right? It could be a tape measure, it could be some headphones, it could be a cup. I'm just kind of looking around my environment because at some point, it's a purchasable item. So this is going to be our base class, and we're going to actually go ahead and take this generalization and turn it into a specialization through extension, through inheritance. So notice first of all that my public class item here contains a single instance variable, which is a private double, and it's called cost. And this will obviously be what the item costs. I've gone ahead and I've set up two public methods. These are the accessors and mutators for the cost value. I simply have a set cost method and a get cost method. And both of these, in this case, I'm using the this keyword just to help start clarifying it. So what I'm doing is passing in a variable called cost, and I'm assigning that variable to the instance variable cost that's contained up here. Okay, and I'm doing the same thing here. I'm adding the this keyword in this case just so you get used to seeing it and just so that we can clarify a little more its use. So that's our class. Now I'm going to go to the driver. What you're going to notice here is that I instantiate a single instance of my item class. I'm going to go ahead and set the cost of the item to $50, and then I'm going to go ahead and I'm going to get the cost so that it's printed. So if we compile that and run it and make a little bit more space here so you can see, you'll notice that it prints out 50, which is fantastic and the most boring program ever. So this is an item, and like, what's an item? We don't have like generic items. You don't go to the store and be like, hello, I'd like to purchase an item. Usually what you do is you go ahead and you say, hey, I want to purchase some sneakers or a sneaker or whatever. So what I've done here is I've gone ahead and created a new public class. I've called it sneaker, and now I'm going to inherit the behaviors and the properties from my item class. So sneaker is going to extend item. And guess what? There are no instance variables and no methods in this class. Why? Where are these instance variables and methods going to come from? Well, they're going to come from the parent class items. Let's go back to our driver and let's change this. So the variable will be of data type sneaker. I'm going to call the sneaker constructor. By the way, there is no constructor in sneaker. Where does the constructor come from? There's no constructor in item. Where does the constructor come from? It actually comes from the fact that Java gives you the default constructor if you do not include a constructor in your class. The default constructor does nothing then other than basically hand you back a memory reference to the object. It does no initialization. So then I'm going to call the set cost method. These are expensive sneakers, so we'll put 250. Maybe they're collectibles. And then we're going to go ahead and we're going to print get cost. I'm going to recompile. I'm going to go ahead and run the application, and we get $250. But you're going to say, wait a second. The object stored in A is now a sneaker object. The sneaker object has no methods. It has no instance variables. It has no properties. But it does, because it gets them via inheritance from the item class. Now that we've seen how the sneaker class can inherit behaviors and properties from the parent class item, let's go ahead and add some unique behaviors to the sneaker class. I'm going to write a simple method, going to make it public. It'll be returning void, and all I'm going to do is call it walk. And what's going to happen is when you walk on this, it's simply going to print out the string squeak, squeak, squeak. Since they're new shoes, they probably squeak. So now I've added to the sneaker class a method called walk. So I'm actually adding to the functionality that I'm inheriting from item. So let's save that, go back to our driver, and make some changes. So now what I can do is I can add, in addition to setting my cost, in addition to printing that cost afterwards, I can say a.walk, and it'll print out for me squeak, squeak, squeak. And again, we'll make this a little bigger so it's easier to see. So you can see all the code in the run window. So notice now what I've done is I've got $250 printed out from prior, and now I'm calling my new method walk, which I actually wrote exactly in the sneaker class. So now the sneaker class gets all of the functionality of the item class and can add to it on its own using any behaviors that we write into that class. Now that we've looked at adding behaviors, let's go ahead and let's add to the sneaker class an additional property. Sneakers are their unique kind of sellable item, so what we're going to do is we're going to put public, and we're going to have an odd set of sneakers here. We're only going to sell them in whole sizes. So we're going to have an int for size, and then what we'll do is we'll actually have public void set size, and we'll simply, this dot size equals size, and we'll pass in a variable. And we'll be able to go ahead and demonstrate that that actually works. We also should probably have a getter. So public int get size. These get a little boring to write, but they do have a purpose, and we do want to make sure that we get into the habit of adding them. Sometimes in real-time simulation situations, we kind of forego this whole process of encapsulation. There's really a trade-off there in terms of safety versus speed, and I guess you can think about that, in terms of cars. The slower cars tend to be the more safe cars. A lot of sports cars tend to be a little bit on the dangerous side. So anyway, we've got that set up. Now we can go back and we can just make sure that this actually works by going into our driver and saying, a.set size, we'll make them like a 12, and then we can go ahead and we can print them out, and we can just say a.get size. So now what you've seen is that we can actually add behaviors and properties to existing classes through this concept of inheritance. So I've added both properties to this object and behaviors, which is really nice. Now let's talk a little bit about two situations that might arise. The first I'm going to talk about is this idea of what's called variable shadowing. And I'm going to put in here, don't do it. What is variable shadowing? Well, if we go back up to our item class, notice that our hierarchy of objects already has a variable called cost. And you've already got a method called setCost and a method called getCost. So sometimes you'll see students come in and they'll do something like, oops, I made this public, let's make it private. We'll make something like private double cost. Well, guess what? Now you have a variable named cost in your sneaker class, and you have a variable named cost in your parent class. That can be a really dangerous situation, because if I'm dealing with my sneaker object, what I'm really doing is I'm actually going to have two different cost values. So, for example, let's add our squeak, squeak, squeak. Maybe we also want to print out, and just to make this point, I'm going to call getCost, and we'll put a value here so we can say what it is. So you'll notice that when I call getCost, which is a method that I'm inheriting from the parent class, and then I'm also just going to print this .cost, which will actually have no value in it, but Java will actually put a value in it for us. So we can see that I've actually got two variables called cost. So let's go back here and just compile these. And what I'm going to do is hit run, and you're going to notice two things. Notice that it printed 250 because that's what I set the cost to, and notice that that value is related to the cost variable in the parent. And notice the one that printed 0, 0, because I just said this .cost, is actually referencing the variable called cost that is associated with the sneaker class. So one is associated with the item class, one is associated with the sneaker class. This is really, really unbelievably, horribly confusing, so don't do it. So let's talk about a situation where it is acceptable to override something in a child class that exists already in a parent class. Let's talk about this concept of method overriding. We've already talked about method overloading in this class. Method overloading is this concept where you have two methods in the same class that have the same signature, and it allows you to set up two methods with the same name that essentially have different parameter lists. And those parameter lists can vary by data type, the number of parameters, or the order in which the parameters are passed into a method. When we get into a situation for method overriding, okay, this is a situation where inheritance is involved. So let's write a method up here. And if we look down in my sneaker class, I've already got a walk class. Let's say that in my, for some weird reason in my parent class, I also have a method called walk. And it'll say something like, hey, I'm an item. I don't walk. So guess what? in my parent class, I have a method called walk. It has the exact same signature. In other words, the name and parameter list is exactly the same as the method called walk in my subclass, in my sneaker class. Well, what does this really mean? What it means is that if I call the walk method on a reference variable that is referencing an object of data type sneaker, I'm going to get this instance of the walk method. But if I call the walk method on an object that is of instance type item, I'm going to get this walk method. Because what's happening is I'm actually overriding the method in the child class. And this is a great situation where sometimes the parent provides a great interface, in other words, a method that you want to implement in your child class, but it doesn't necessarily work the way you want it to. So you have the ability to completely override a method in a child class. So let's run this. And first of all, we'll just run it. And notice that nothing's changed. Right? I still get my squeak, squeak, squeak. Squeak. I don't even know if that's how you spell squeak, but we'll stick with it. But now I'm going to do something a little different. And let's say I create a new object called item I equals new item. I'm now going to create an instance of the item class. And all I'm going to do is come down here. I'm going to say I.walk. So in this instance, I'm calling the walk method of a sneaker object, which inherits from the item class. In this instance, I'm calling the method walk on the parent class. So we'll just run it, compile it, make some more space here in the run window, and notice that the call to a.walk still gives us the squeak, squeak, squeak of the new sneaker, but the call to I.walk basically gives us the method call from the parent class. So one of the things you have to remember is that the type of the method, the type of the reference variable, the data type of the reference variable has a definite effect on what methods get called. And you need to be careful when you call a method on variable data types. Now, we're starting to get into some ideas here about polymorphism, and we're kind of looking at that right now. But let's do one more thing. Notice that I have a method here called, obviously a class called item. It has a walk method, it has a set cost method, and it has a get cost method. In my sneaker class, though, I have these set and get size methods. So what happens if I were to accidentally say on my item object, what if I called I.getSize? Well, if you notice, item doesn't have a method in it called getSize, but its child class has a method in it called getSize. So, I mean, hey, that should run, right? And I get an error because it says, hey, I can't find this symbol. There's no getSize method in the item class, and that's correct. Remember that inheritance is a one-way street. Okay? A parent class doesn't know about methods in its child. A child class does know about methods in its parent because it inherits them. Okay? So that's really important. So we'll comment that out, delete it, and always remember that situation. Now, what's actually occurring here? I said before that we have polymorphism occurring. Well, guess what? I've got this item object, and I've got this sneaker object. But now I'm going to do something really, really crazy. A sneaker is an item. It extends the item class. So I'm going to make a new item object called myItem. And guess what I'm going to do? I'm going to put a sneaker object in it. Well, this is weird because never before in Java programming have you probably ever seen the data type of a variable disagree with the type of data being put in it. But does that really occur in this situation? Because a sneaker is an item object, right? Because sneaker extends item. Is an item a sneaker? No, and we'll see that in a second. So let's compile this to make sure we're sane. And we're good. But now we can actually go ahead and say, okay, well, does it work the other way? And I can't type either. Well, let's compile it and take a look. And I get an error. It says incompatible types. Well, wait a second. If I can put a sneaker into an item variable, why can't I put an item into a sneaker variable? And that, again, is because a sneaker is an item. An item is not a sneaker. Okay? So there's this process where you can have any of the children or any of the subclasses in a hierarchy save themselves into the reference variable of a superclass or the parent class, but you can't go the other way around. So this provides an error. What happens, by the way, now if we look at this, if I go ahead and try to call a method on these. So I've got my item, and I'm going to call the walk method. So the my item reference variable is of data type item. Well, guess what? The my item class, the item class, has a walk method, and the sneaker class has a walk method. So right now, take a second, place your bets. Which method is going to get called? Notice that Java still called the right method. Notice that even though this reference variable is an item, Java realizes that the data inside of that reference is an object of type sneaker, and when I call the myItem.walk method, it actually calls the appropriate method because it knows that it's overwritten. Now, one other thing I can try to do right is I've got this reference variable of data type item. Now notice I've got this method called getSize in my sneaker class. Let's try that method and see what happens. So place your bets. Does this work or does this not work? It does not work because this reference variable to the data type item says, well, the parent class has a method called walk, and let me go see if the child class has a method called walk. Oh, it does. It's overwritten. Well, let's call that one. But in this case, it goes to the item class, the parent class, and the parent class doesn't have a getSize method. It doesn't go forward and look in the sneaker class. It doesn't look in any of the children to see if they have a getSize method. It just throws an error. So this is incompatible. The type of stuff that I'm doing in these lectures is the type of stuff that you need to do as you read the chapter. As you read a concept, you need to play with it, try to break it, try to make it work, and get into this situation where you can learn how inheritance works and how various reference variables that you have to different data types affect the way methods are called on those data types. Let's talk a little bit about the concept of polymorphism, this idea that an object can have more than one data type. In other words, that you can treat an object in more ways than one. So what I've got now is I've gone ahead and I've made an additional class that extends item, and I've called this one dress shoe, and it has its own walk method. So just like sneaker goes squeak, 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 dress shoe goes squish, squish, squish. And if I go ahead and I run this class, you'll notice that I get the results as expected at the bottom, squeak, 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 squish, squish, squish. But now here's what's really interesting, right? Like what if I own a shoe store and I want to maintain an array of sneakers? Well, one thing I could do is say, well, okay, let's have like a sneaker array and call it sneakers, and I can make like a new sneaker array, and maybe I could have like 50 spots in that array, and then I could have like a dress shoes array, and I could call that like dress shoes. There's way too many S's in the middle of that variable name. Dress shoes, and maybe that holds like 50. And then if I want to like print my inventory, I actually have to go ahead and loop through both of these. I mean, wouldn't it be really nice if I could just have like one array that managed all of my shoes? Well, guess what? I can, because my shoes are related via their parent class. They both extend item. So we can actually go ahead and set up an array of items. Let's call it items. And we will create a new array of items. And let's do like 5, because I don't feel like typing all this in. And then what I can do instead of this is I can actually start to add some things here. So I'm going to do this manually, even though it's a little tedious. We'll do cut and paste, right? So what I'm going to do is I'm going to put a new sneaker in the first one. In the second one, I'm going to put a new dress shoe. And then we're going to alternate between sneakers and dress shoes, right, until we get to a full array state. I did not want to set a breakpoint. All right. 3, and then finally, we'll put a sneaker here at the bottom. And now what's cool is, because these relate via a superclass, in other words, because these objects are polymorphic, I can simply go ahead and write an array, write a loop. and I can simply just say items I dot walk. And what this will do is it'll iterate through my items array and call walk on each item. And I make errors too. That should be item, not items, right? It should be the data type, not the class type. And when I run this, let's get some more space here. You're going to notice that it goes through and calls the walk method on each object, and you get the appropriate response from the walk method. And that's what's really cool about when you get into this idea of polymorphism and you have collections of objects that relate via a parent class. There's some really cool things that can be done. I would like to mention a few things that are mentioned in the book, and I'm just not going to bother going over them at the moment in the video lecture, but there are some discussions of object casting and the operator instance of, which is just another way to handle objects in a collection where you might be iterating through the collection and need to determine the data type of an object that's in a collection. I'll also mention that because I haven't necessarily mentioned it at this point, everything in Java is an object. Well, I haven't necessarily mentioned it in this lecture, right? So one of the things that we could do is go ahead and create a new array, say called, and let's say instead of items, let's do that. Let's not do it that way. What I can do is, instead of making this of data type item, every object in Java relates via the object class. But now I'm going to go ahead and I'm going to run this. And I get an error. Well, why do I get an error in that class situation? It says, hey, there's no method called walk in the object class. And that's true, right? Because object is a class that is the parent of item, and that class doesn't have a walk method. So one of the things I need to do in that situation is actually cast my object, and it's kind of a pain in the neck to do it. So I'm going to do is wrap this in parentheses, and I'm going to put an item there, and this should fix it. Otherwise you might see me fade to black, verify some code, and come back. But now notice what I've done is I'm getting the item out of that index of the array. It's of data type object. I'm casting it to an item, and I'm calling the walk method on the item. Oh, and it compiled fine, so. And now I get the response that I expect. So sometimes if the objects in question have a parent class and you want to have a common parent class that may not contain the method or some of the properties that you want to access, and that's the only way you can kind of leverage the polymorphism of those objects, you may need to get into this case where you need to go ahead and cast the objects to the appropriate type. And in that instance, sometimes if you have a mixed bag of objects in a collection, you may need to go ahead and actually use the instance of operator to determine if the object in question is truly an instance of a class that can support the method that you're calling. Let's address a few things that are relevant when dealing with inheritance. First of all, the item class is a generic concept. So it'd be really odd if I could instantiate an instance of this class. I mean, really, what is a generic item, right? A widget. It's a concept. It's not something you can sell. You would be like, here's $5. I would like to buy your generic item, good sir. Or, so this idea here is that we don't ever want someone to instantiate an instance of an item class. So one of the things I can do is I can declare this as an abstract class. When you declare a class as abstract, it means you cannot instantiate that class. So abstract classes cannot be instantiated, only extended. And obviously now if I go ahead and I compile this, I'm going to get an error because I'm trying to instantiate item objects. And you'll notice that it says item is abstract, cannot be instantiated. So if you want to write a class and its sole purpose is to be extended, or that class itself represents a concept or idea, you can declare that class as abstract. On the flip side of that, we could turn our sneaker class, and you could say, wow, this sneaker class is like the best sneaker class ever. I don't ever want anyone to extend my sneaker class. So if you declare a class as final, it means that the class can never be extended. So class is declared final, cannot be extended. And that really won't affect anything in this program, but it's just something that you need to know. So this idea of abstract classes and final classes is an important concept to understand. To close out this lecture, let's talk about the keyword super. And specifically, let's talk about the keyword super in relationship to constructors. I think it's fairly straightforward using the super keyword with methods. So if there are questions about that, please let me know. But let's talk about super and the concept of constructors. Right now I'm using the default constructors in both of my classes. I've gone back to my original driver here. I've gotten out of the one that has an array involved in it. So what I'm going to do is I'm looking at my item class. This is my parent. I'm going to go ahead and I'm going to add a constructor. Okay, so this is my class. And what I'm going to do is I'm going to make an item constructor with no args. And I'm going to go ahead back to my driver and compile. Oop, not driver 2. Let's close that out. And I'm going to go back to my driver and I'm going to compile it. And everything's cool. Everything's good. Why? Because, well, I basically rewrote in my item class what is essentially the default constructor. It does nothing. It accepts no arguments. And if I look at my child class under item sneaker, it doesn't have a constructor declared, but the constructor of the child and the parent must agree. And what do I mean by that? Well, I'm going to change my constructor here to accept a double, and I'm actually going to force people when they create these objects to go ahead and set the cost. So I've changed my constructor in my parent class. So I need to come back to my driver, and actually when I go ahead and create my item now, I'm going to pass in a value. Let's make it $444 so it's obvious, and I'm going to compile. And it seems to work. And when I go to run, though, notice I don't get a compile time error, I get a runtime error. I get the method, that exception in thread main, java.lang, item method init v not found. Alright, so I'm getting an error for my sneaker method. Well, that's kind of odd. Well, here's the deal. The constructor in the item class requires that I pass it a double. The sneaker class has no constructor, and it extends item. Well, guess what? Anytime the constructor in the parent class requires a parameter, you need to give it the parameter. In other words, the child class needs to pass parameters up to the parent. So if you have a parent class that has a constructor that accepts parameters, you have to go through the process of making sure that the parent class gets the parameters at once. So now I need to have a constructor in my child class. So we're going to go with public. I'm going to call it sneaker. And I am going to build my constructor framework first. And what I need to do is pass in a value called double. I'm going to stick cost in there. And now here's how I appease the parent class. I call super, which is, hey, go to my parent class, tell its constructor, here's the value that it needs to actually get its job done. So the idea here says super by itself calls the parent class's constructor and allows me to pass in any values that I need to pass into that parent constructor to make it happy. So let's go back to my driver class. And now for sneaker, I'm going to have to pass in a value. So let me pass in like 777. And down here, I might need to put another one in because this is going to be a problem. I'll put in 888. And obviously, I'm overriding like the cost and stuff, so there might be some weird output here. But now I'm going to compile. Compile's fine like it did before. I hit run, and now I don't get any runtime errors. And notice that, oh, by the way, I'm overriding the cost here in 250, right? Oop, yeah, let's get rid of that so we can see this. So one more time to prove that it works. You'll see that the number that comes up is 777. So I've got a $777 pair of sneakers, which is kind of expensive. So I pass this value into the sneaker class. That value is put into this cost variable. That cost variable is then passed to the item constructor via the super call. That value is then put into this variable. This variable is then assigned to the instance variable, and we're all set. Yes, if you have a very long hierarchy of objects, you must have super in every single one of those. So anytime the constructor of a parent class requires arguments, you need to, in the child class or the subclass, pass those arguments up the hierarchy of inheritance, the chain of inheritance, via supercalls. In this lecture, we're going to take a look at some of the basic elements of Java. We're going to look at data types. We're going to look at basic input and output. We'll look at comments and talk a little bit about mathematical operators, reserved words, kind of the functional syntax components of the language. So let's start by building on a basic program that looks very familiar to what we did in previous lectures with the Hello World program. This one's called Basic Java Elements. And what I'm going to go ahead and do is, the first thing I'm going to do is put 2 slashes into my code. These are called comments. Any single line that follows 2 slashes, notice in JGrasp it's going to turn orange for us, is what is called a comment. So I'm going to zoom in a bit on that. And what you'll notice is that there I can leave notes to myself. So let's do basic data types. And what I'm going to do is leave comments throughout the code to help you follow along with what each piece of this code is doing. Because you're going to notice that we're going to have multiple lines in this program. And in your case, if you were to leave comments in your code, what you would more than likely be doing is leaving notes to yourself. So in 6 months when you come back to your program, you remember what it does. Or if other people on your development team read it, they know what the code does. But for now, I'm just going to use comments like this. These are single line comments. There are multi-line comments. Notice if I just start typing, the text is black. That means that it's not a comment. So what's cool about single line comments is I can put anything behind them and they're actually ignored by the compiler. They will not be converted to machine code. They're literally just sticky notes in the code for the programmer. So let's take a look at some of the basic data types. So I'm going to go with our simple system.out.println program that we did before. I'm going to put the statement in there. And we're just going to print to our main output window, which in this case is going to be the JGrasp console, some different types of output. So first type of output we have is what's called an integer. And an integer is a basic data type in Java. It's a whole number. So make it simple. It can be positive, it can be negative, but integral numbers are whole numbers. They have no fractional point. So the easiest way to recognize them is they have no decimal. I'm going to copy and paste this. There are many more of these, by the way, in the book. What I'm going to do is look at the popular data types. Okay, so we'll just look at the more popular ones, and then you can go through the book and determine some others. Doubles are numbers that do have a fractional component. And in this case, you can tell a double from an integer by the fact that it has a decimal point. So fairly straightforward, right? Anytime I talk about an integer, I'm talking about a whole number. Anytime I talk about a double, I'm talking about a number with a fractional point. Again, they can be negative. Other data type that we will deal with are called booleans. Unlike numerical values, booleans can either be true or false. And notice when I type the word true, it turns blue. Purple, and you'll notice that true is a reserved word of the language. We talked about that last class. Notice that public static void, public class, these are words that turn purple. They're reserved by the Java programming language because they have special meaning to the Java programming language. Okay, so I'm going to go down a little bit more. I could also print out false if I wanted to, and actually I'll make a note of that. They're the only 2 values. Boolean, by the way, means 2. Well, it doesn't really, it's after George Boole, but you can start thinking of anything that related to George Boole, like binary values, Boolean algebra, true or false. Some other languages use yes or no. Some other languages use 0 or 1. In Java, it's just true or false. And then finally, we've got 2 others. We've got characters. And characters are going to be any single character between single quotes. So there's the character C, and I'll copy and paste a few more. And here's the character 1. There's a difference. Actually, let's use 7. Notice the difference. We'll back out here a little bit. On line 18, I have the character 7, and up on line 8 I have the integer 7. Okay, the item on line 18 is the character 7. It actually just means print the symbol that represents the quantity 7. The line number 8, where I have the integer 7, actually says give me the quantity 7. They're both actually represented by different underlying binary values, and as we get more into binary, we can talk a little bit more about that and data representation next week. But notice that the character 7 is different from the quantity 7, and you know this to be a fact. You could write down that you have 7 air conditioners on a piece of paper, and that symbol 7 just represents how many, but then if somebody made you carry 7 air conditioners, you'd realize that they're heavy. One is the actual quantity of items, the other is just the symbol that represents the quantity. So after characters, we can build on that, and we can actually have strings. Strings are a series of characters pulled together between double quotes. And you'll notice that, again, strings are just, think of like if you've ever made decorations in kindergarten or whatever, where you took some string and you put some popcorn on it, and you strung the popcorn together and hung it up to make a nice decoration. In this case, we're stringing characters together. Strings always come between double quotes. Characters always come between single quotes. One odd thing that confuses people, though, is you can actually have a single character string. So now on line 22, I have the string C, and on line 17, I have the character C. One is a string, one is a character. What's the difference? Well, technically one's an object, one isn't. But as we move forward, you'll notice that there are some subtle differences. There's different ways. Strings are actually a robust data type called an object that we're going to talk about as we move forward in this class, and you can actually do more with objects, whereas a character is what's called a primitive data type within Java. And actually, that's really a good point to take a look at. Let's change the title up here. So instead of basic data types, let's talk about these items as primitive data types. And then down here, we'll start to get into objects. What makes something a primitive data type? A really good example of thinking about primitive data types would be to think about the periodic table of the elements. This idea that what makes something an element is that it can't be broken down any further. I mean, it's already the smallest component or quantity that can be, unless you get into molecular components, obviously. But in this case, an integer, it's just the number 7. We can't break it down into anything else. A double, it's 7.14. We can't break it down into anything else. A Boolean is true. We can't break it down into anything else, right? They're primitive data types in Java. They are the smallest component they can be. A character, C, the character 7, they can't be broken down anymore. In the case of an object, in the case of an object, something like a string, notice that we can break a string down. We can break this down into its constituent characters. Okay. Notice in this case with the string C, although you say, well, you can't really break that down any further. What I could do is actually break that out into a single character. All right. So the double quotes indicate strings, and the single quotes indicate characters. And hopefully, as we work with those more, some of that clarification some of that'll come through a little bit better, and we'll talk more about it too. So these are the basic data types in Java, and once we get the basic data types together, we can go ahead and we can start to do some things. So let's take a look real quick at one process that we can utilize, and we'll call it concatenation, if I can spell it. Concatenation is the process of gluing two data values together. In Java, the concatenation operator is the plus sign. So one of the things that you've noticed in all of my system.out.println statements up to this point is I've only been printing a simple item, like true, C, the 7, hello class. What if I want to glue some stuff together? What if I wanted to say something like, a character, and next to that statement, print a simple character statement, or print a number, or later on we're going to actually be getting input from the user, and what if I want to go ahead and I want to add that user's input to my output? So I can customize hello world and make it say something like hello Jason. Well, in Java, all we do is put a plus sign in there, and then the item we want to print. And you'll notice what I've done here on line 28 is to go ahead and glue the string a character : space to the the string, a character colon space, to the character C. So this process of gluing things together inside of a print statement, later on we'll do this in other places, is called concatenation. And I'll just put gluing two items together. Well, it's usually a string. And what's nice about concatenation is it allows us to customize our output. So this process can work for other things. You should probably be asking yourself the question at this point, what happens if I try to concatenate two numbers? Well, guess what? We haven't talked about mathematical operators yet, but if you try to concatenate 2 plus 2, you're going to get 4. All right, so we'll look at that output. And then let's do one other thing, and we'll actually glue the string 2 to the string 2 and see what output we get. So let's actually go ahead and run this. I'm going to compile that. And then I'm going to make a bigger window down here. We're going to run the program. Let's scroll up. Now, first item we should print out, we should get 7, we should get 7.14, we should get true. So let's see how we did down here. 7 printed, 7.14 printed, true printed, the character C printed. You can see that both in the window at this point. 7 printed, hello class printed, the C printed. But here's what's cool, right? When we get down to concatenation on line 20, notice that a character colon C printed because we glued the C to the previous character. Did I have to do that? No, but I just wanted to demonstrate the process. Notice that the item on line 30, when we concatenate two integer values, the plus sign actually has a different meaning. It means actually add. So notice the context of the operator, or the plus operator in this case, changes how it operates. And notice at the bottom, when we concatenate two strings, we get 22. The idea here is that there's some context occurring. So you need to be aware of your data types when using the plus operator. So in this case, you might expect on line 32 that you would glue two items together, but in this case, because on the left-hand side of the operator, on the right-hand side of the operator, you have integer values, you end up actually getting math. In this lecture, we're going to discuss selection statements. This is going to be a very brief and to the point lecture because I don't want to make selection statements any harder than they need to be. They're actually very simple from a syntactical standpoint. The real difficulty with selection statements is trying to figure out the puzzle of the logic involved in solving the problems. So really what we want to do is think of this more as, kind of a word problem in math and less about the actual programming implications. That's why in this lecture we're going to use some logical diagrams. So briefly we can think of a selection statement as a piece of syntax that changes the flow of our program based on logical expressions. Up to this point, we've been asking the user to enter values. Now we're going to be able to start to use selection statements to make some decisions about those values. For example, if I ask the user to enter their age and they enter a negative number, well, that's a really bad thing because people should be positive numbers in terms of their age. So we could actually make a statement that says, hey, you entered an incorrect value, you entered a negative age, we're now going to terminate the program. We haven't gotten to loops yet, so we don't really know how to go back and ask them to re-enter those values, but we could at least make a decision to terminate the program. So with selection statements, we have some control. We could also do things like, if somebody enters the wrong PIN number, we could also terminate the program, or if they enter the correct PIN number, we could actually remove money from their bank account. If we wanted to write an ATM machine, we now have the capability to determine if the user has enough money in their bank account, then we would allow the withdrawal. If they don't have enough money in their bank account, then we would deny the withdrawal. So we can change how our program is operating based on logic. Now, decisions. Simply put, computers can only compare two things at any given time. They can either say, is this true or is this false? So if you have a complex decision that you want to make in the computer, what you need to do is break that complex decision down into the much simpler decisions that it's composed of. Complex decisions, even though you may not think this in your brain, are composed actually of many simple binary decisions. In other words, decisions that are yes or no decisions about a bunch of things. Something as simple as, should I take an umbrella today? You might think that's a fairly simple decision, but it's a complex set of factors involved. involved, you're probably asking yourself, is it raining outside? Yes or no? No, it's not raining. Is it sunny outside? Yes or no? Well, it is sunny. Did the weather person say it might rain today? Yes or no? Do I really feel like carrying an umbrella around today? Yes or no? So something as simple as taking an umbrella with you on any given day is actually a series of very tiny decisions strung together that end up in your ability to decide if this is a path that you would like to take or not take. And that's why we need to think of all decisions in a computer system. Is this true or that true? Okay. Is this true or that true? Okay. Is this true or that true? And eventually through all of these little decisions between two things, we'll be able to get to the end of the branch where we actually want something to occur. So the takeaway is always break all of your complex decisions down into simpler decisions, which can often be a challenge, and that's really the challenge of this chapter. If we're using flowcharting, we have this diagram here in front of us that we can think of. The diamond in a flowchart means, hey, a decision is being made here. So you'll notice in the blue diamond in this slide, is this statement true? Your program's running, it hits a decision point. And at that point, the computer's going to ask, is this statement true? Is the user over 18? Yes, the user is over 18. Then we can allow them to sign up for a car loan. So it would go to the right and go to the yes branch. So is the user over 18? Nope, they're 16. Well, we can't sell a 16-year-old a car because they can't sign contracts, and if they wreck it, we'd have to eat the loss. This is what that statement looks like in pseudocode. This is not actual Java, but it's close enough to help us decide how to go about writing the real program. So notice we have if this is true, and this is true. That statement is actually between parentheses. In Java programs, as you've seen in the book and in other resources, that's where we put the expression. That's where the question is. And if that is true, we do the top part of the equation where it says do this. If what's between the parentheses is false, we do what's on the else branch. So we can compare these directly. We can say that if the statement in the blue diamond is true, we go to the yes side. In this slide, if the statement is true, we do what's on top. In this slide, if the statement is not true and we go to the left and we go down the no branch, then we would go to the else part of this statement. Okay, now what do we replace do this with? Well, actual executable Java code. And what do we replace this is true with? A valid expression. Do you always need the else statement? Like what if, something's not true, you don't do anything? Well, in this case, we don't always need the no branch. You don't always need the else branch in a decision. So your program runs, it gets to the statement, it says, hey, is this statement true? If it is, go ahead and execute some code. What if the statement is false? Don't do anything. If you are not the millionth customer at the grocery store, they don't do anything. If you are the millionth customer and balloons fall from the ceiling and noisemakers go off and you get lots of money. So you don't need a false branch unless you actually need it in terms of logic. A couple other things, if we want to make complex decisions, our program can have multiple if statements, and they can be nested inside each other. So we come down, we make a decision. It says, hey, is this statement true? If the statement is true, in this case, it's going to go ahead and it's going to end up at another decision. So we can actually have multiple decisions nested together. I could have easily put that decision under the no branch, but in this case we have multiple decisions, and we can actually have one decision then lead to another decision, lead to another decision. So this idea of breaking a problem down into multiple decisions and then putting them together in a way that, by the time we get to the end of that chain of decisions, produces the output we want, is definitely possible. Here's what that looks like in code. Notice the yellow code, in this case, represents the innermost decision on this slide. So in other words, the second blue diamond that's inside of the yes branch is represented by the yellow code in this slide. So you can actually see where the nested if statement exists and where the outer if statement exists. And what you'll realize is that the only way we'll get to that yellow code is if the first question or the first expression in the first set of white parentheses is true. Otherwise, if it's false, it just gets all skipped and we get to the else statement. So make sure you're comfortable with seeing how this flowchart represents or is represented by this code. What are the comparison operators in Java? One of the reasons why I've been trying to keep you from saying the word equals when using a single equal sign is because that is the assignment operator, And in this case, when we're trying to compare two things, the equality operator is actually two equal signs. So if we're trying to say is 7 equal to 9, which you would never say because it isn't, but you would use equals equals. So two equal signs is the way of asking Java, are two things equal to each other? And then greater than and less than, you've seen before. If you want to determine if two things are not equal to each other, it's an exclamation point and equal sign, and then there's also less than or equal to and greater than or equal to. And a point in the big blue arrow on the right-hand side. One thing you should know is that these operators are only for comparing primitive data. In other words, comparing things like ints, doubles, and characters. If you need to compare strings or you need to compare objects, then you need to get to the next slide. So let's talk about comparing objects. The only way you can compare two objects is if those objects provide a behavior, and again the formal word for that is method. The only way you can compare two objects is if those objects provide a method to compare themselves to other objects. So you'd have to look at the API, you'd have to look in the book, and see if each object provides a way to compare itself. And you'll notice that in the string class, it actually provides the equals method, and you'll see that in my sample code. So if an object doesn't provide that functionality, there are ways that you can actually write it, and we'll talk about that later on in the semester, or you just have to deal with the fact that you can't compare two objects. In other words, what are we doing when we're comparing two objects? We're comparing the properties of those objects. If you use primitive operators to compare objects, what you're really comparing are the memory addresses that they point to. Remember that object variables don't contain the object, they just contain a memory address where you can find the object. Sometimes we actually want to do that. We want to see if two variables are pointing to the same object, but more likely than not in this class, at this point in time, you do not want to go about using primitive operators to compare objects. You always want to use their built-in comparative method. Java also provides if, else, if, else constructs. These are very nice when you're trying to put together chains of related logic. And so what's really nice about these features, if you're trying to compare a large number of, or make a large number of decisions based off a single value, the first expression that's true will terminate the entire if, else structure. And you'll see that in the book, that it's a nice way to short circuit a bunch of decisions. I mean, if I'm trying to find a student in the class, and I happen to find, I say, hey, are you Jason? And you're the first student I ask, and you say, yes, I'm Jason. Then why would I continue to ask the 19 other people in class if they're Jason? It makes sense that when you find the first person, you stop asking. And in the case of if, else structures, as soon as you find a true expression, all of the other expressions are skipped so that the computer can save some processing time. The idea here is why keep comparing things if you found a true answer? And that if that's the functionality that you want, then this is the construct for you. Switch statements are just a convenience for creating if, else statements that are only switching on a single value. A lot of times in computer programs you'll see like enter P to print, S to save, D to delete, A to select all. So in that case you're asking the user to enter a single character, and based upon that single character you're going to execute a series of behaviors. So what you want to do here is the switch statement is if you don't really understand why you're using them, you can actually just choose not to use them. But if you take a look at the programming code that accompanies the lecture, you'll notice that I do have some examples. I show two parallel sets of code, one being an if, else statement and a switch statement that achieve the same ends. Another thing to mention is the Boolean operators are discussed in the chapter. Building complex expressions using the and or operators is not actually required. They really just provide you with a convenience for chaining together a series of decisions inside of the parentheses in an if statement, in other words, inside of the expression. So for example, we had this program logic flowchart earlier on in the lecture. So notice that I've got two decisions, and earlier on we represented this by two nested if statements, but I can use something like the logical and operator to go ahead and kind of make this a little bit more syntactically compact. So in this case you'll see that the second and this is true. The yellow component here is again representing the inner decision in this statement, but you'll notice that it's a little bit more simplified. There's actually some issues with this code, but I've oversimplified it. Actually, if you can find the errors, you could always just post that to the discussion board. But there's a couple things I'm leaving out here, but I'm really trying to simplify this to demonstrate that you can get this type of structure into less space by using the and operators in this case. In this lecture, we're going to talk about static methods and static variables and how they differ from instance methods and instance variables. Let's start with a little bit of a definition, and then we'll move on to a visualization of what we're talking about. When I use the term instance variable and instance method, or even the term instance itself, what I'm talking about is an actualization or a concrete realization of a class. In other words, an object. We've used the new operator and we have gone ahead and constructed an object in memory. So for each object that we build using the constructor and the new operator, we are basically making unique copies of any properties that that object has in memory. In other words, we know that each object has state and it also has behaviors. So every time we make an object, what we're doing is we're making unique copies of those state properties and those methods in memory. One of the things I'm going to point out in this lecture is that I'm going to keep saying that objects have their own copies of variables and methods, but when it comes to methods, that's not exactly true. There's some memory management that happens in the Java virtual machine, and so we can imagine that every concrete object, every instance of a class has its own copies of methods, but it's actually managed in memory a little differently. So just pretend with me for this lecture. So let's visualize an object. I keep saying to you that objects have state and they have behavior. And I just said to you that an object is an instance of a class. So this circle is going to be how we want to visualize each concrete instance of a class. In other words, something that we have actually built and exists in memory. Objects are often visualized with this diagram. You'll see it in a lot of different books and on different websites. If you may have already seen it already in some of the reading I've assigned. So here's the deal. Important methods go in the blue area, and one of the things you'll notice is that inside of that blue area there are a bunch of what I'm going to call instance variables. These are the properties of your object. In other words, these are what track the object's state. Notice that the properties are protected. If you think of this like a castle, you can think that the methods are wrapped around the variables. In other words, last lecture we talked about this idea that we want to keep our instance variables or keep our object state private so that we can protect how those properties are actually modified or changed so that they don't have any errant values added to them. What's really nice about using this type of visualization is that we can really see what I mean by encapsulation. Again, this idea that the state of our object is protected by methods and that we as the programmers can scrub data as it comes in and out of our objects so that we know that the state of our object will never be put into a situation where it's corrupt. So again, in the blue area, we have important methods. Inside of that, we have properties. So here's a class, really basic account class. We're tracking one property, account ID, and we've got one behavior that allows us to get account ID. So on the right, you will see how that appears using our new object visualization. So I've called the constructor on this object, and now I've got one in memory. So I have one copy of the account ID variable in memory, along with one copy of the getAccountID method. Now I'm going to call the constructor again, and this time I now have two copies of the account ID in memory. And because account ID is of data type int, we know that in Java it takes up 32 bits of memory. So right now I've got two copies of account ID, so I'm taking up 64 bits of memory. Let's call the constructor again. Now I have three objects in memory, therefore I have three copies of the account ID property in memory, right? Taking up 32 bits times 3, right? 96 bits of memory. So what we've got here now are three different copies of this object. That means we have three unique copies of account ID and three unique copies of the getAccountID method, or at least that's what we're going to tell ourselves at the moment. So let's reinforce that idea. Three unique copies. Every object instance, if that variable is an instance variable, in other words, not tagged static, every variable that is contained in an object will be created anew every time we construct the object. So for every object, we will have a unique copy of each piece of each instance variable that is being used to track that object's properties. So how does this differ from static variables? Well, static variables are a little bit unique. Whereas with instance variables, we have one copy of each property for each object, static variables are shared amongst all instances of a class. Therefore, there's only ever one copy of a static variable in memory. And a couple of properties that you'll see as we play with these is that we can change static variables using both static and instance methods. Let me say it again. We can change static variables using both static and instance methods, but notice that we can only use instance methods to change instance variables. And as you play around with this, you'll realize that it makes sense. So let's visualize this. Here's the same class we looked at before, but now I've added a static method, or sorry, a static variable. And if you look, I've still got my standard getAccountID object up there on the right, and it's got its single copy of the account ID property in memory, but you'll notice over here in this little cloud, which I have to represent another location in memory, I've created one single copy of the type variable. And we know that that type variable is actually tied to this object. So we want to maybe be able to access that type variable. So I went ahead and I added another public method. Notice that this is an instance method. Therefore, the account object now has two methods associated with it, a getAccountID method and a getType method. This is also to enforce the fact that instance methods can access static variables. So we've got an instance method that lets us see that. Notice again, there is one copy of account ID with this one account object, and now there are single copies of the getAccountID method and the getType method. Let's go ahead and create another object. Now I've got two copies of the account ID property in memory, and I've got two copies of the getAccountID method and two copies of the getType method in memory. But notice I still only have a single copy of the type variable in memory, and this will continue. The more objects I create, there will only ever be a single copy of the type variable in memory, and that means that static variables are shared by all instances of a class. And if one object changes that static variable, then it obviously changes for all of those things. And the example I always like to use is like an end-user licensing agreement. If the objects are programmers and Apple goes and changes their agreements for, programming an app on the iPhone, then it changes for every programmer. So there's only, in this case, one copy of the type variable in memory, and it is shared by every object or every instance of that class. So what are static methods? Well, a couple things that we want to talk about first. Static methods can only modify static variables, and when you think about it, it kind of makes sense because you don't want your static methods to be able to reach into a single object instance and make changes. The other thing about static methods is that they are associated with the class and not individual objects. Same as static variables, by the way. They're associated with the entire class and not, say, a specific object. The other thing that we'll notice is that when you call a static method, you call it with a class name and not with an object reference. So in this case, we've already seen the use of static methods, and this is why it's really important for you to start capitalizing class names. So how do we call this thing? Well, notice I've added a new method in this case, and it's public static, and it's called say hello. And when you call the static method, all it does is print hello. And you'll notice the way I've called it is by using the name of the class, account with a capital A, and say hello. Also notice I put the say hello method into my little cloud to indicate that now there will only be one copy of this method in memory. And again, we're just visualizing this idea of copies of methods in memory to help us understand this topic. So a couple notes and reminders. Instance methods and static methods can change static variables, but static methods cannot change instance variables. Read that a few times, pause the video. It's an important thing to remember. Static methods are often used like classic functions if you come from a procedural programming background. Oftentimes I see people get into object-oriented code and they want to make everything a static method because they're used to functions from other languages. What's really nice though is we can use this power in a sense to provide processing that should not be tied to an instance. And again, if you look at the math class or the string class, but the math class is the best example of an entire class that is just existing for the purpose of providing you with some basic math functionality. I believe everything in that class is static. So take a look at the math class to see how why they've chosen to provide a purely static class that allows you to just process math functions in a way that you may need in your program. And also take a look at the string class to look at what they've made static and what they've left as an instance method. And that's really the best way to start to understand how to separate what should be static and what shouldn't. So in the real world, we can think of some examples of what is an instance variable or method and what is a static variable or method. So again, just to kind of simplify all this, when we say instance variable or method, what we mean is that these items are related to a specific object. And let's say like my car, it's one car, it's my car, the transmission breaks. My transmission broke, yours car is probably still running fine. Let's say I have a pet goldfish. My pet goldfish dies. Well, if you have goldfish, your goldfish are still living, because these are instances of transmission and a single instance of a goldfish, and they're only affected that single instance. And if I'm drinking a soda and my soda goes flat, well, your soda didn't go flat. You might not even have opened it and started drinking it yet. So these are instance variables or methods. Single instances, things happen to just that one instance. Now we think about that in relationship to static variables or methods. These are items that are related to an entire class of objects. So if there's a product recall, let's say for example you've got a crib for a child, they're always being recalled. Every single crib that was made by that manufacturer gets recalled. So that is a static, something that is, the recall or the on that item or the warranty on that item is tied to all instances of that class. In PA, we pay sales tax on classes of items. You might choose to store that sales tax in a static variable, so you don't have, 5 billion copies of a double in memory that just tracks 0.06. And in that case, if you also wanted to change the sales tax, if it changes, which it probably will at some point, you only need to change one variable instead of iterating over billions of objects and changing the sales tax for each individual object. So again, sales tax is related to a class of objects and not a specific object. Next thing would be like if you're in a union or a collective labor, collective bargaining situation, you might have a labor contract, and that labor contract is one contract that is tied to everyone who works under it. So again, many instances sharing a single contract. So these are kind of some things that are just instance-ish or static-ish. So hopefully this quick lecture was helpful to you. And if you have any clarification or need any additional clarification, please post to the discussion board and take a look at the reading and let me know. Thanks. So by request, I'm going to present a video lecture here on proper syntax use in Java. There's been a lot of questions about how do we use curly brackets, when do we use semicolons. So my plan here is to build a Java file and to walk through most of the structures that we've talked about this semester. One of the problems with Java syntax is you kind of do just have to memorize where certain things occur and use code as an example. So let's go through each of these. I'm going to start by building this file, and I'm going to name my class, we'll call it syntax. Now, a couple things. Notice how I immediately put in my beginning and my ending brackets for the class. All of our program is going to be written between these two curly brackets. Notice also, again, that I'm following the convention of capitalizing the name of my class. So, inside of those curly brackets, I'm going to hit the tab key, and notice how my cursor's moved over a tab stop. Usually when we nest things inside of curly brackets, we tab over because it makes it easier to see. Now, before I even go that far, notice how I'm using this format for matching up curly brackets. Some people find this to be a bit difficult. This tends to be because I come from more of a scripting background than a formal programming background. So for this lecture, what I will actually do is I'm going to switch from a format that I normally use, and I'm going to line up all of my curly brackets along a left alignment. So notice in this case, this set of curly brackets is the opening and closing set of curly brackets for this entire program. Okay, now I'm going to tab in. I want to nest something between the outer statement. You can kind of think of curly brackets as enclosing paragraphs of information if you really want to use that metaphor. So I'm going to go ahead and set up my main method. Don't ask why I think I need to capitalize it. And now I'm going to go ahead and immediately put in the opening and closing curly brackets that are associated with my main method. And a couple of people have asked, what is the main method? And the main method is officially the entry point for our program. In other words, later on in this semester and in other programming courses, you're going to have multiple classes, and when you run the program's going to go, well, where do I start? There's 10.java files here. Which one do I need to start from? And the main method is really what we call our entry point. Okay, and it's just something that Java expects to see. So now I'm going to go inside of this set of curly brackets. Before we even move there, notice no semicolon at the end of line 1. Notice no semicolon at the end of line 5. All right. So in this case, these components. This is a method, and this method specifically is encased by curly brackets. The class definition is encased by curly brackets. We haven't actually used any semicolons yet. So what I'm going to do is actually go back up to line 1 and use an import statement. When we use import statements, okay, they end in a semicolon. So you just kind of have to get used to that as well. Now let's go ahead and start using some more complex constructs here. I'm going to declare a variable, and I'm going to set it to 0. Notice that when I declare a variable, I end that line with a semicolon. A few other things to notice in my code is notice I'm putting a space between my variable name and the assignment operator, and a space between the value I'm assigning to the variable and the value. And notice I put my semicolons directly behind the line. So semicolon is more like a simple statement. If you want to think of curly brackets as being separators for paragraphs, you can think of semicolons as being periods in a sentence. Okay? So simple statements end with semicolons. There are exceptions to every rule. So now let's go ahead and set up an if statement and talk about how if statements. And we'll say if I is, just some random number less than 10. Now, a couple of people have noticed that in an if statement, you don't need curly brackets. And I'm going to put I is less than 10 in here. The only time you do not need curly brackets, so if statements do not need curly brackets if there is only one simple statement beneath the condition. So in this case, the condition is the expression that's inside of the inside of the parentheses. And notice that's something else you need to realize, is that in an if statement we use parentheses, not curly brackets, to indicate the condition. Now a lot of people were confused because they were setting up if statements and then they were doing things like this and having two statements. Now, here's the problem. When you don't use curly brackets with an if statement, the only line that is associated with the condition is the line immediately after it. If you have multiple conditions, and let's copy this so we can have multiple examples here. I also want to make sure that I keep everything lined up, and I'll make this file available for you. So I'm going to remove this. This is valid, okay, because I have one statement beneath my condition. This is invalid. What's going to happen is line 18 is associated with the if statement, line 19 is not. How do I go about indicating that I want both of these lines to be associated with the if statement? I wrap them in curly brackets. What this does is it forces the compiler to see these two lines and make these two lines associated with this branch of the if statement. What's the best way if this confuses you and you're not sure how to deal with this? Well, I'm going to go ahead and add another line up here. Make sure I get all my formatting correct for you. To avoid confusion, always use curly brackets with if statements. It's a few extra things to type, but I think what you're going to find out is that it makes understanding the code a little bit easier. So, semicolons and simple statements. Single line if statements do not require curly brackets, but you should use them anyway to help you format your code. Again, notice every time I'm inside a set of curly brackets, I indent. Also notice how easy it is to say, oh, line 20's curly bracket is opening, and line 22 curly bracket goes with that, and it's closing curly bracket. So notice how this formatting that I'm using is really key to how I'm setting up my code. So what if we wanted to do an if-else statement? Well, let's see here. We'll use curly brackets for multiple lines of code associated with a condition. So what if we have an if side to the, well, we've got an if statement. What if we have an else statement here? So we'll stick with our friendly neighborhood first example. Notice that because I only have one line beneath the else statement, I don't need curly brackets. So we'll say same rules of curly bracket use apply to if else statements. But you should still use curly brackets. And so what I'll do is copy this and give you an example to look at that. And how would we do this? Well, let's use my same way of formatting. It takes up a few more extra spaces. Remember, white space is any character that actually adds some space around your brackets or your code. So in other words, I'm using a new line character to help me line these up. And notice how easy it is to see that these curly brackets go with that else statement, and that these curly brackets go with that if statement, and things are disassociated from one another. Okay, so I'm going to also indicate here, always use curly brackets in the beginning to avoid confusion. We can go up here, and now we can see how this looks with multiple statements. So we'll do same example, but with multiple lines of code and an else statement. And you can probably guess at this point how I'm going to format this. And I could have copied that and pasted it. So there are some examples for if statements and how we actually go about formatting them. What if you have an if statement inside of an if statement? The same rules as above apply. So let's set up an if-else statement. So if I is less than 10, we'll jump down in here. And let's say if like I is between 0 and 10, right? So I'm going to set up another if statement. We'll say if I is greater than 0. Notice how I tab in and how easy it is to see that this if statement is associated with those two curly brackets, and that this if statement is associated with those outer curly brackets. So I'm using vertical alignment to help me identify how my curly brackets match up. By the way, notice the only place I've used semicolons in any of this code is at the end of my lines, because in if statement use, we're not too concerned about semicolons. So let's move on and look at loops. And what we'll do is we'll just continue to use my variables. Hopefully all this compiles, but it's more about syntax at this point. So let's take a look at a while loop. So while I is less than 10, notice just like the if statement, notice the only difference really between a while statement and an if statement is that the while statement uses the keyword while, and if statements use the keyword if. So notice there's no semicolon here. Notice I have a set of curly brackets around here. Notice that if I only had one line after the while statement, I could forego the curly brackets. But guess what? I'm going to tell you always use curly brackets with loops to avoid confusion. Okay, so I'm not even going to show it to you without them. .out, .println, I is. Then what we'll do is we'll do I++, and now I've got two lines after the statement. So that's why I went ahead. Notice again, no semicolons. Now let's look at a do-while loop. Remember, what's the difference between a do-while loop? Do-while loops check the condition after the loop executes and not before. Okay, so think of it like this. I may have said this in another lecture, but a while loop asks questions first and then shoots. Think of like an old Western, right? So they always say you can shoot first and ask questions, or ask questions and shoot. Ask questions first and then shoot, or shoot first and then ask questions. In the case of a while loop, we ask questions first. We check the condition and then we continue on to check the executed code. In a do-while loop, we actually go ahead. You know what's interesting is, I'll have to see if I remember the syntax. I always get Java syntax confused with other pieces of with other operating systems. So we'll just go here. All right, and what I'm going to do is copy and paste this into my do-while loop. And the other thing I'm going to do is notice that in my last piece of code here, by the way, I was increasing I, so I is now equal to 10. I'm just going to reset I to 0. So what happens here is we go to the do statement, we enter into the body of the loop, these two lines are executed, and then we get to the while and the condition is checked. Now, here's some odd syntax. The only time you ever see a semicolon after a condition is in a do while loop. So I think I could always be wrong on that. There are other times, but in this case, they would be kind of odd if you did it. So in this case, there's this little hanging semicolon here. It took me forever to remember this. Again, notice how I format my code in this case. If I want to, let's be consistent. This curly bracket is associated with this curly bracket. Notice how my tabs, notice I'm consistent, by the way. If you scroll up in my code, all right, you'll notice that there's a nice vertical lines along tab stops. These are my nested statements. Moving in and down, you see the next line of code. If I had more code, they would be nested over and using tabs. Think of like an outline. It allows your eye to easily follow. Notice I use white space between these. Notice I'm using comments. Notice there's an aesthetic to writing code. So do while loop should look like this. Again, the do while loop is kind of like an odd exception, so you just have to remember how to set it up. I'm going to use J for this, just because I can. Now I'm going to use a for loop. And I'm going to go back and grab one of my lines of code here so I can avoid typing it again. And get this set up. You should, oops, that was weird, have some type of, you really should be paying attention to how things are formatted. So for loops have unique syntax inside the condition, but everything else should look familiar. I type fast but not accurate. So notice that I've got a for statement, I've got a condition inside of parentheses, I've got my curly brackets, there's no semicolon, but there's no semicolon after my condition, right? But inside of my condition, it's a specially formatted one just for loops. So to the left of the first semicolon allows me to initialize my loop control variable. To the right of the first semicolon is my condition to determine how long my loops should execute. And after my second semicolon, I have a variable incrementer. In other words, in this case, it's going to walk my variable from 0 to 10. And actually, you know what? There was a question about can loops go backwards. So let's go from 10. All right. To 0. And we'll do J minus minus. So this loop will go backwards. So count down from 10 to 0. Actually 10 to 1. So this is the format for a for loop, and this is how I expect you guys to format your loops and your if statements. Switch statements are probably the one last thing that's a little bit weird. Let's see, like a good switch statement would be char my character. Let's just set up a little variable here. I don't really need to do it this way, but just kind of demonstrate it. We'll switch off of the my character variable. Now, the big question is going to be, notice like the way I format my code is very hard for me to set things up. Question is, can I actually do this off the top of my head? The reason I'm asking is I'm writing a lot of Objective-C code at the moment, so let's see if I can do this. And let's not teach you to format this like that. Let's do that. So for switch statements, I'm going to compile this and make sure I actually got this right. Actually save my file. See if this actually compiles. Didn't see any mistakes. Look at that. No mistakes. Syntax lecture with no mistakes. I'm going to run it. And I did get my syntax right. So let's explore the switch case syntax now that I know I'm exactly correct. I've got the keyword switch and a condition, and notice this is the same as my for loop, the same as my if statement. I have a statement identifier, I have a condition followed by a pair of curly brackets. Inside of the curly brackets, I have a case statement, and again, this is one of those odd places where you're going to have to make some memorization if you choose to use case statements. Case is the keyword, followed by the item you want to review, followed by a colon. There aren't a lot of colons used in programming languages, but the semicolon is probably more predominant. But in this case, a colon is the proper operator in that case. I have multiple lines. After that, notice there are no curly brackets associated with this. Notice the break statement is in there. Notice the default statement follows that same format. So let's throw a case in here to match the variable I just set up. And we'll also do one that does a capital A, just for, completeness with the case statement and fun stuff it can do. Again, what's more important here is the syntax and the layout. A lot of people have been asking, like, okay, where do I put curly brackets? Notice that I could, there's nothing stopping me from putting curly brackets anywhere in my code, right? It actually will compile. This is correct. In fact, sometimes you might use curly brackets for like a syntactical separator in some of your code, just more like to help you organize things, but most of the time you won't. What's most important is to take a look at this file, memorize the rules of where curly brackets go. If you're confused about where they go, use them everywhere that they're required. All right, so as I scroll back up, I see a lot of people setting up if statements like I have here on line 14 and 15, and it confuses them, right? Because they think that they don't ever need curly brackets. So that when we get to line 19, 20, 21, and 22, this is the more proper way. If you get into using curly brackets everywhere they're required. I may have missed some syntax here, so if there's something missing, let me know. We can address it on the discussion board. But I just meant this to be a quick walkthrough, not the most organized lecture. It's very specific, so hopefully this is helpful to you. If you still have questions about formatting, I'll post this code along with this video lecture, and it's important that you also take time to look at how I format my code, look at how you format your code. I don't put out an official style guide in this class, but I expect that you look at what I do and mimic that. Proper formatted code goes a long way. You would never hand in an English paper that was just a bunch of random sentences on paper, unless it's kind of like a postmodern graphic design course or some type of modernist literature course or something like that. So take a look at how these things are formatted. This will give you the rules for using syntax. And if you have any questions, please ask.